So the title says coding theory and DNA storage. So these are two fields that are maybe not familiar to every one of us. I also thought the audience was quite mixed, so it should be more of an introduction. I try to keep it light. Also, my background is from mathematics and coding theory, so to all the chemists, biochemists, and people that are more expert than me in DNA, I'm sorry for very simplified wordings and pictures of it, but I just want to give the idea clear. Okay, so let me start the talk with the why. So digital data storage is a very known topic to all of us. So we stored over all the years digital data in several ways. So probably all of you know USB sticks, CD-ROMs, SD cards. Maybe not all of you know punch cards or magnetic tape, but yeah, this is just a little timeline where we went through the time. Also, we see that we managed to get from 80 bytes per punch card to several terabytes on a USB stick, so that's quite good. We can store more data. Why do we want this? Because the amount of digital data that we are producing is growing rapidly worldwide. So if you think about 2010, we had something like 2 zettabytes, which, if I'm not mistaken, is like trillion, or 1 zettabyte is like a trillion of gigabytes, which to me is already difficult to imagine. And last year we had about 180 zettabytes. So it is growing very rapidly. And the devices that we have, they don't exist forever. So the durability for a USB stick is roughly like 30 years or so. So we need to replace them every now and then. And we also need to be able to store more and more data. So what do we want to do? We want to use DNA, because we know that on our DNA, a lot of data is stored on a very tiny space, actually. So we want to use this idea. And the first person to introduce this was Richard Feynman in 1959. And the first successful experiment of encoding data on it came then roughly about 50, 60 years later. But these experiments, they were only successful in storing the data on the DNA, but not getting it back. And usually if we want to store data, we also want to get it back, right? But luckily, just 2 years later, a group at ETH Zurich actually managed to get a fully successful scheme. So they were able to store data on DNA and then get it back by using Reed-Solomon code. So an encoding scheme that comes from coding theory. So why do we like DNA, or why is it a good candidate? So it has 2 key properties. One is it's extremely durable. If I'm not mistaken, we can still recover DNA from mammoths. I think there was a paper on Nature. Also, it's very dense. So as I said, we can store a lot of information on a very tiny space. And this is a very big advantage to other devices that we have. I think a professor once told me, you can store basically the whole internet on a string like this of DNA. That's kind of amazing. So everything sounds very nice, very promising, but there is, of course, a but. We have a lot of challenges. So for now, writing on the DNA and reading it back for now is very costly. Of course, the prices decrease, but this is still a drawback. Also, the coding schemes that we have for now are okay, but not good. So we need better coding schemes. And of course, the complexity and scalability of these things yet is not good enough. So here is where coding theory comes in. This is a rough outline of what I'm going to talk about. I know it's a bit dense, I hope to manage in time. First, I want to make sure that we all speak the same language. So let me start with a little bit of the basics in DNA storage. So for the people, especially from this morning, you can sleep for now and wake up a bit later. Let us introduce DNA. So maybe from high school, you remember that DNA is built of 4 bases, which we denote by ACGT for the nucleotides. And if we combine them together, then we get a DNA strand or an oligonucleotide. And now I am speaking of digital data, or let's say usually we work with binary strings, and we want to put these or convert these into DNA. So we can just choose a conversion however we like it. For example, I can say A is 00, C is 01, and so on. And then I can convert any string of DNA into, or any binary string like this, into a DNA string. as simple as that for now. That's the basics. So how do we actually write on a DNA? Let's say we have a message or a file or anything that we want to store. Then we transform it first into a binary message or a binary string, or several binary strings actually here. Ooh, okay. Now we use this conversion, I would say, to DNA strands. So we go to this further step, and we do this in a structured way. So if you see here, we have several binary strings, and somehow in the whole process, we want to be able to say which one was the first one, which one was the second one. Remember, as if you had files and you want to say, I want to access the first file. So we use some index here, which this one would refer to the first, then the second, and so on. What we also do is, and we need this later for sequencing, is we add something that we call a primer. Now, again, I am not a chemist or biologist, but the primer basically is a starting block from where it knows where the sequencing process can start. So this is just helpful in the further steps. Okay, once we have written on a DNA, we actually want to build the DNA. So we know now theoretically how it should look like. So we use synthesis, which is the writing process. So we artificially create or generate this DNA strand. Now we have to do this base by base. And also from one string just written like this, we cannot create just one DNA strand, but we create thousands of copies of each. This process is a bit slow and also a bit noisy because there are chemical processes and things that can happen. And also due to technological limitations, we can also only generate DNA strands of roughly 200 bases long, so rather short if you compare it to nature. Okay, but we can do so for now. So we can actually create DNA strands, but that's just the storing part. Now, at a certain point, we wanted to retrieve back what we have. So we need to convert this process. And this is DNA sequencing. So the part of reading out what is actually written on a DNA, the basis of the DNA. Now, luckily, this is a bit less expensive than synthesis, still expensive, and a little bit faster also. And again, of these thousands of copies, we generate thousands of reads. And also not every read here is equally represented here because PCR has some bias on certain strands. Also, again, errors are introduced during sequencing because of the structure of the DNA. Depending on what bases are in there, there are some biases and errors can happen. There are several technologies like Illumina or Nanopore, which maybe some of you might have heard. I'm not going into details there. Yes, but eventually what you get is a lot of copies of all of your strands, not in the equal proportions with errors. Now, I spoke a lot about errors that can happen. How do they actually look like? So let's say we have a DNA strand. There are 3 types of errors that can happen. One is a substitution. So that means a base gets just changed with another one. If you are a coding theorist, that's the usual type of error that you're dealing with, except for erasures, but this is usually the kind that you're looking at. But we have 2 other types. One is a deletion. That means a base, here in that example, the C, gets just completely cut out, and the positions, they move on, like they close here the gap. Oh, here. That means we have no clue about the position where it got canceled if we just see the output. So this is, for a coding theorist, again, different to an erasure because we lose the information of the position and where it actually happens. And the counterpart to deletion is an insertion, so it can just happen that a base gets inserted here. Okay. That's for the basics. How do we do coding theory, or how should it work? So, of course, you can also have any combination of all of that. That's the scheme in general. So a binary data file gets transformed into DNA, gets stored somehow with some chemistry, and we get 1,000 multiple reads, noisy reads, and we want to retrieve back the binary data file. Now, in this talk, I just put this as a black box. I call it a channel to make it look more coding theory-like. And what is different to coding theory, usually we get one noisy output. Here we get a whole bunch of it. So we try to understand how we can deal with it. This leads me to error correcting codes. And now for those of you who are coding theorists, you can sleep for a bit and the other ones can wake up. So just one basic slide, what is coding theory? The main task is to ensure reliable communication. How do we do this? We add redundancy. So usually if I just send my words as they are and errors happen, then at the receiving end, I could understand a completely valuable word, but the conversation would not go on because there is misunderstanding. So what can we do? We can add redundancy, meaning we can just repeat 3, 4, 6 times the same message. And if then an error happens, this is not a valuable word, and this person would understand, okay, most likely this one here was sent. Of course, we cannot repeat 100 million times because that is a bit useless. So there is always a trade-off of how much redundancy do I add to this whole scheme. So a little bit more abstract, we have an information, it's going to be encoded, then sent through a channel where an error can happen, and we receive something which hopefully we can decode back. Or so to say, we can say we have an alphabet and a code, which allows us to give a little bit of structure and which allows us to get back to original message. That means structure-wise, we have here code words, which are all the allowed words, and our received word can lie somewhere in this whole space, hopefully close to a code word. And if it is close enough, and by close enough, I mean in a certain region, which I highlighted with this ball, then we are able to decode correctly. Now, this region is given by something that we call the minimum distance. There are several ways of computing the minimum distance. There are several distances that we can consider. And whenever we have errors about roughly half of this distance, then we can correct uniquely. But there are also tools to go beyond that. Here in DNA-based data storage, what we are looking at is not the Hamming distance. It is usually the Levenshtein distance, which would count the minimum number of insertions or deletions that you have to get from one to the other. So it's a little bit different. There are also in DNA storage other distances like the edit distance, which would also include substitutions, but this is something, the Levenshtein distance is a very popular distance to look at. Okay, so this about the basics of coding theory. Now, as I said, substitutions are the usual type of coding theory. So what I want to show you today is more deletions and insertions, because these are the things that classical coding theory cannot handle until now, or not very well. So a deletion channel, or if we want to call it this way, looks as follows. We have some input sequence X. Now this is 8, has a length of 8, and it gets sent through a channel. And then some positions would be deleted, maybe with some probability. And we get an output Y, which now is just 6, has just a length of 6. So 2 deletions happened. Now, as I mentioned already before, this is different to an erasure channel because we don't know where the deletion happened. If you look at this example, we could either have canceled this first one or this second one here to get still here 1 position. So we don't know. There are several options. Also, we call the output Y a subsequence of X because it's kind of obtained from X by deleting some points. Now, since we don't know the positions, we have to look at the whole picture. What are all the possible outputs? And we call this a T deletion sphere. And if you think back of the image that I showed you before, we want to try to build these spheres around our X's to see how much they overlap and if they overlap. So the T deletion sphere would just be all the sequences, all the subsequences I get from X by deleting T positions. Let me do an example. Okay, so this is our input sequence 1, 0, 0, 1, 1. And let's say we look at 1 deletion, all the outputs that I could get. So I can delete the first one and I obtain this sequence. I can delete one of the 2 zeros and I get this second sequence. And I can delete the last 2 and I would get the last sequence. Now, I already gave you an idea how this works. So we can just cluster into something that we call runs. So just sequences of the same elements. And then for the one deletion sphere, the size of it is exactly determined by the number of runs. Very easy, very simple. Unfortunately, if we extend this to any bigger t, we don't know the exact size. So if you are interested, one open problem is to study the size of a deletion sphere. Now, I told you insertions and deletions are kind of the counterpart. So you may think, okay, that must be the same for insertions. But this is not the case for insertion. We immediately know the exact size. So deletions are a bit more tricky because they depend a little bit more on the center. And by center, I mean the X where you start with. Okay, again, why do we need the spheres? We want to say when is a code able to correct deletions or insertions. So with these spheres, we can define a T deletion correcting code. That means a C in our alphabet space is a T deletion correcting code if whenever I take any two distinct code words and I draw these spheres around it, they don't overlap. So we have no overlap here. Then in that case, C can correct T deletions. Now we also want to understand what it means to be able to correct T deletions. And Levenstein in 66 was able to show that if a code is able to correct T deletions, that is equivalent to saying it can correct T insertions. And that is also equivalent to saying it can correct any combination of T insertions or deletions. So in this case, again, we can treat them again similarly. That's why usually people introduce just one of the channels because it's easier. Okay, so we know the basics, but are there codes? Are there T deletion codes? So that's one question. And for those of you who fell asleep, I have a little intermezzo or a riddle to let you think a bit. So let's say we have 10 bags. They all seem to be the same. They all consist of coins. All the coins also to you seem to be the same. Now, the trick is 9 bags are exactly the same. They all contain coins of a certain weight, omega. But in one bag, all the coins have just half the weight. Now you have access to a digital scale, which you can use exactly once. How do you determine the bag that is corrupted in a way? Okay, I give you a little hint. So we can just measure once. So somehow we want to use all of them together to get a relation. We know that if they all had the exact weight, or let me start from this. We enumerate all of the bags. This is bag 1, 2, 3, and so on. Let's say the corrupted bag is bag I. We just give it an index. Okay, now from the first bag, I take 1 coin, from the second 2, and so on. So I get a weighted sum. If they all had the correct weight omega, then what I would see on my scale is 55 omega. But there is a corrupted one. So I have 55 omega minus I times half of the weight. And then you can divide by the weight what you see, and you get back your index. Okay, does that make sense? So this little riddle is exactly the motivation for the Warshimov-Tenengold codes. So these are defined in the following way. So these are the binary version. So the binary Warshimov-Tenengold codes are defined by all the binary words of length n, such that their weighted sum is equal to A modulo n. Now these codes can correct exactly 1 deletion or 1 insertion, as we have learned. And if you think about it, why does this work? So the weighted sum, or this here, the checksum, makes sure that we know what should get out. Like before, we know that the overall weight should have been 55 omega. The I makes sure that we know about the position. And the CI makes sure we know about the value. And then the N is to make sure that no position over all the N get lost. So that's the high level idea, but there is also the math behind it. Okay, can correct 1 deletion. And the good codes are always the codes that have a lot of code words. And actually, if you choose A to be 0, so the checksum to be 0, then these are the cardinality is biggest. Also, there were some results still by Levenstein. He did a lot of work on that, that if we denote by A the size of a largest single deletion binary code, then it grows roughly as this value here, as n grows large. And we want to have optimal codes in this kind of sense. And there is a conjecture that VT codes with 0 checksum are optimal for any positive integer. So it's a conjecture because it has been shown for some values, but not mathematically proved for all of them. So we want to construct good codes. But now you tell me, okay, one deletion is nice, but is it realistic to correct just one deletion? Probably not. So we want to correct more. What about more than one deletion? Well, there are code constructions. They are not optimal, they are suboptimal with respect to the redundancy, but there are. But if you're interested, this is still ongoing research, so we still aim to constructing codes that can correct more than one deletion or insertion. There are some works that are kind of close to, so there is a lower bound on the redundancy that we want to hit, and there are some code constructions that go pretty close. That's, I think, the best yet known so far. So if there has been new updates, please let me know. Exactly. And also, we don't just look at maybe deletions, but also just fractions of deletions or probabilistic scenarios. So there is a lot of research going on. As I said at the beginning, there are not yet so many good error correcting codes for this scenario, apart from one deletion. Okay, so that's about where coding comes in. But we are also interested in the retrieving process. So if we go back to this picture, I said that here we have thousands of copies for each of the strands that we use. So the first one has thousands of copies here, thousands of erroneous copies also. So this is also different to coding theory because usually we have just one noisy output, but here we have many. So how do we deal with this? Well, the naive approach is we use inner and outer codes. How do we do this? So these are our strands. Then first of all, we would use an inner code, meaning we add redundancy to each of the strand, protecting each strand and at a nucleotide base. But this is not sufficient because a strand can also get completely lost. How do we deal with this? So we look at it as, oh, sorry, the colors are not too strong, but we look at this as a collection and encode this whole collection. So we add an outer code to it to actually deal with losses or something. This approach works, but it has still drawbacks. So it's still suboptimal with respect to redundancy. It's a slow process. It goes to every strand singularly, which is not really good complexity-wise. So what can we do? We can use clustering. So we can try to cluster those outputs with similar properties that have to be defined, like good properties. So we use first clustering and then try to find from there the coding point. Also, we can look at it theoretically. So there is a theoretic reconstruction problem. Now, for one example, so it's a large family. Actually, there exists a large family of reconstruction problems. The most famous is again by Levenstein, but also trace reconstruction. You can do this whole thing in a coded way, in a non-coded way, but the basic principle is the following. Let's say you have one input, which you send through a channel several times, and you get T different outputs. And the question is, how can you recover from all these output X? So as if we had from the deletion channel before, many outputs, they are all different, and we want to say from which sequence do they come from. And also we want to know what is the sufficient number, like how many of these channels do I need to reconstruct this sequence? Now, this is a problem that has been largely studied in various scenarios for various channels. various situations for not only deletions, but also insertions, but also burst errors, sticky errors, whatever you can imagine. So a lot of work has been done here. Also in combination with clustering. So you would do clustering first and use the reconstruction problem then on each clustered part. Yes, exactly. Okay, I think my time is slowly running out. So I showed you a little bit the basics first and what coding theory makes or what is missing yet to do. But there are also a lot of other different directions, coding theory related questions that you can ask. So other applications and directions are synchronization errors, where you also lose packages sometimes. Random access problems, where you want to specifically ask for a file or a data. Then we can also use modern codes such as LDPC codes or polar codes to decode insertions and deletions. I think some work has been done there to deal with it, also in a convolutional kind of setting to deal with the shifts. It can be used to identify proteins. We had the work on reconstruction with fluorescence to make sure proteins can be identified, still very theoretical and abstract. Also, you can go more specific into the sequencing part, like nanopore sequencing, and look at decoding there as a window decoding, because it cannot go base by base, but always considers windows. There is the question of composite DNA, many things, even cryptographic application. Lately, we tried to use it for authentication schemes and build a framework, a security framework for authentication with DNA as like an in-product thing to identify, I don't know, products like clothes or something. Yeah, there are many different ideas that you can work on. I hope you got something out of it and that it is a bit more clear, or the coding theoretic part of it. And with this, I would like to conclude my talk. I thank you very much for your attention, and I'm open to answer your questions.
Thank you very much for a nice talk. Any questions?
Thank you. I do have a very basic question. So you listed the different error patterns, deletion, insertion, but what about classical erasures? I mean, like you have a molecule you can't really identify. Is it possible in DNA, or so that you know where the error is, but you can't just read it?
As I am aware of, you don't know, so it gets deleted or not, but it's not like, because it immediately reattaches again. So.
Okay, thanks.
But there maybe the chemists know more.
Yeah, thank you very much for this interesting talk. So it seems this problem of multiple insertions is open for many years, because the early work was from the 60s, right?
Yes.
So is there a chance that, I mean, are there new approaches that where this problem is tackled now, in the last, let's say, 10 years, where there are new developments, was there some progress?
You mean by new progress, new codes that could deal with more insertions and deletions?
I assume then is a new approach needed first, because if you work on that for 40, 50 years and nothing comes out,
yeah, that is a fair question. And this is basically what my work would consist of. Yes. So we try to use also other codes, I mean, these are all, or VT codes are not linear codes, or they are linear over the residue ring, but generally you try to use completely different codes to cope with this. But yeah, there is progress there, but still, I think a lot of work has to be done before this is actually working.